Superposition theorem is applied to linear circuits. Then what is linear circuit? Linear circuit means that the current is proportional to the voltage. So when the current change, the voltage change, but they change proportionally. So let's look at the example here. Let's look at a resistor. The voltage along the resistor is proportional to the current flow through the resistor. As we know, the Ohm's law is V equals I multiplied by R. And most importantly, R is the resistance. The value of the resistor, which is resistance, is a constant. It does not change. Superposition theorem saying that a voltage across an element or the current flows through the element is the algebraic sum of either the voltage or the current of the element due to each independent sources acting alone. Now let's look at an example here. Let's look at this circuit. The circuit involved with a voltage source and the current source. They are all independent sources. When applying the superposition theorem, we are only considering the independent source. The controlled source are not into the play. In this case, there are two independent sources. Let's consider the voltage along R3, so VR3. VR3 contains two parts, VR31, that's part 1. That is a voltage with only the voltage source acting, the current source being taken out. So this is VR31, and plus, this is the algebraic sum, plus the second circuit with the voltage source being taken out. Okay, there is only one source, which is the current source acting along here, and we obtain VR32. That's part 2. Notice that this is not VR3 squared. It doesn't mean squared in this case. And then VR3 then equals to this two parts plus together. This is a meaning of superposition. Next, let's look at how we considering each independent source alone, one by one. How do we do that? Let's look at the first part. The first part of the voltage VR31. So VR31 is the voltage that this voltage source acting alone. So we need to remove this current source or turn off this current source. How do we turn off the current source? If we want to turn it off or we want to remove this current source, we want the current goes to 0. So how the current goes to 0? It has to be open circuit. So there's a terminal here. So if I have A and B here, and A and B here, so nothing in between A and B, it is open circuit. This is how we turned off or how we remove the current source. So let's go back this example, this terminal and this terminal, the current source being removed. The current source is open circuit. Now this circuit only contains one independent source, which is a voltage source. Then VR31, VR3, that's 1, that's part 1. It's easy. We obtain the current flow this loop because every resistors are in series connection. We can obtain VR31 very easily here. VR31 here. Remember the notation here. This is VR31. So that the current is V divided by R1 plus R2 plus R3. And then the voltage is the current multiplied by R3. So this is a VR3 part 1. let's look at part 2. Part 2, we're going to consider this independent source, which is the current source. And at the same time, we're going to turn off this voltage source, or other words, to remove this voltage source. And how do we do that? How do we turn off the voltage source? Here is how we turned off the voltage source. The voltage is V. We want to turn it off, which means that we want the value of this voltage source goes to 0. So which means we want V equals to 0. If V equals to 0, how do we do that? It has to be short circuit. If we have this point A and this point B, which is A, this is a B, it has to be short circuit here. So how do we short circuit? We use an ideal wire connect point A and point B. So this is how we remove the voltage source or to turn off the voltage source. Now let's look at the circuit again. So we're considering this current source alone. We do not want to consider this voltage source by the superposition. So we need to turn it off. We short circuit the voltage source. So which means that we use an ideal wire to connect this point to this point. This is a short circuit for the voltage source. We only have one source here now, which is current source. Now we need to calculate VR3 part 2. If we notice that all R1 here in this on the right hand side of current source here. What is connected between point A and point B? R1. Look at this two resistors here, R2 and R3, they're in series, so I combine them together. So R2 plus R3, that's this resistor. And then if we look at this two resistors here, this two resistors, these two, they are in parallel again. Notice that these two circuits are equivalent. They are equivalent completely. To obtain the voltage on VR3 in this circuit, using Ohm's law, VR3 2 part 2 equals to R3 multiplied by the current flows through this resistor R3. VR3 2 equals to I naught multiplied by R3. I naught, that's the voltage along R2 and R3 divided by R2 and R3. VR is the voltage between point A and point B. This is exactly what I marked here. That's VR between A and B. From this circuit, VR equals to the current I multiplied by this two resistors in parallel. So R1 in parallel R2 and plus R3. We can obtain VR3 part 2. Of course, we can use the current division to obtain the current flow this branch R2 and R3. Here is marked as I2 in this circuit. So I2 equals to the total current is I. And then once you find I2 and VR3, you multiply by resistor. So what's the final result? The final result, the voltage along VR3 contains two parts. The first part is the voltage acting along. We call it VR31. The second part is VR32, where this current source acting along. So we obtain VR31 and VR32. We sum them up algebraically. Whatever the value it is, we sum them up. This is VR3 using the superposition theorem. One thing we need to notice when we apply superposition is about the treatment of dependent source. The superposition theorem only applies independent source, the independent current source or the independent voltage source, but we do not turn off the dependent source, the controlled source. We do not touch them.